I guess if you have any questions, you can ask Ali, right? We start today looking at the phase lead compensator, which is kind of dual to the phase lag. So let me first introduce the phase lead compensator. If you want to look at some notes about the lead compensator, take a look in Canvas. Okay, in Canvas, there are some notes, just like there are notes for the phase lag. And so there's a folder called Frequency Response Design. Okay, frequency response design. And there's a file in there called, I think it's called lead design. So that covers the underlying theory. There's also a PowerPoint presentation that will cover the material that we're going to look at on Wednesday. I think it says phase lead example. The keyword there is look for example, and this is a PowerPoint file. I think it's, take a look at that, okay, in preparation for Wednesday. But today what I wanted to do is take a look at the, basically the underlying theory, the circuit, and then I'll kind of give an overview of design approach. And then on Wednesday, we'll go ahead and do an example. All right, so it's the phase lead. So the lead compensator, let me describe its transfer function. And the form that we're going to work with, it looks like this. It's going to look like, we've got a parameter K. We've got a 0 at omega z, or just call it Z. And then we have another parameter at a pole at omega p, or just call it P, like this. Okay, so we have basically three parameters to deal with. This looks a lot like the phase lead, phase lag, I'm sorry. It looks very much like the phase lag, except with the phase lead, the pole is going to be at a frequency greater than the 0. Okay, so this is the opposite of the lag. Okay, so with the lag, we had the pole was less than the 0. This is a lag. But today we're looking at this. Okay, so that's really the key difference when we look at the transfer function. So if I just look at this, I can't tell whether this transfer function, I can't tell whether it's a lead or lag. I have to look at it more closely. The form is the same for both cases, but with the lead, the pole is at a higher frequency than the 0. So let me sketch the frequency response. I'm going to sketch here. I'm going to sketch the magnitude response on the Bode diagram. So this is the frequency, omega. And so we're going to sketch over here the magnitude. The units are in dB. And over here, we're going to sketch the phase. So this will be the angle of the compensator in degrees. Again, this is in frequency omega. So we have a 0 and a pole. So omega z is here, and omega p is here. So the pole is at a higher frequency than the 0. And so the magnitude characteristic looks like this. It's flat until it hits the 0, and then it starts increasing at a rate of 20 dB per decade. And then when it hits the pole, it flattens out again. The low frequency gain, let's take a look at the gain at low frequency. When omega is small, when S is equal to j omega, when omega is very, very small, when S is very, very small, this goes away and this goes away. And so the low frequency gain is K. So this gain down here is K. except we have to convert it to dB. Okay, this K is related to this K. This is in dB. And then the gain starts increasing right here. Okay. Now we have over here a similar sort of idea. We have the 0 and the pole. And what's going to happen is that the phase characteristic is going to look something like this. It's going to increase like this. Okay, so that's the straight line approximation. The actual curve just looks like a hill, looks something like this. Okay. Now there's some characteristics here that we need to be aware of. The more we separate the 0 and the pole, the higher this hill becomes. It's going to start off at low frequency. At very, very low frequency, again, let's remove these two terms, and we see that the phase is going to be equal to 0 degrees. Okay. At very, very large frequencies, it doesn't matter what omega z and omega p are. If this is huge and this is huge, you get huge over huge. Again, is approximately 1 again, and so we're back to 0 degrees. But in the middle, we get right here, we get a positive phase. Okay, I'm going to call this distance right here, I'm going to call it theta m. Okay, m stands for maximum. Where's the maximum? And it occurs halfway in between these 2 points right here. I'm going to call that omega m. Okay. Now there's some equations for these characteristics, and also here I want to take a look at. Let me first take a look at the phase, since I drew that most recently. There's a relationship that tells us that sine theta m is equal to alpha minus 1 over alpha plus 1, where alpha is equal to the ratio of the pole over the 0. Now remember, the pole is greater than 0, so this is a number greater than 1. Okay. That tells us how high this mound of dirt is relative to the spread here. Now usually in design, what we need to do, we're going to try to improve the phase margin. So we want to basically, if we don't have sufficient phase, what we want to do is we want to add phase lead. We want to anticipate what's going on. And so we design for a certain theta m, and then we have to try to figure out what alpha is. So usually in design, we pick theta m, and we seek the value of alpha. So alpha is the unknown in our design. So it helps to resolve this problem, resolve this equation in terms of alpha. Here we have theta described in terms of alpha. You can do a little bit of algebra or a little bit of trig. A little bit of trigonometry and algebra yields an equivalent equation. And the equation tells us that alpha is equal to 1 plus sine theta m over 1 minus sine theta m. So this is one of the design equations that we are going to use. Okay? So in design, we pick this number. So since we pick this number, then we can plug it into our calculator and figure out what is the separation, the necessary separation between the pole and 0 as a ratio. Okay. The other thing that we need to understand is, where does this peak occur? Where does this peak occur? Okay, this omega m. And so omega m is geometrically, on a piece of paper, halfway. Okay, it's geometrically halfway between omega z and omega p. What I'm saying is, if I drew a picture here and said this is omega z and this is omega p, then I go halfway in between, and this is omega m. Okay, so if I gave you two numbers, and I say, what's halfway in between them, how would you find that? Take the average, okay? But we have to remember, what kind of scale is the frequency response on? Log scale. So we have to take the average in a log scale. And so what we get is that because this is a log scale, we get that the log of omega m is 1/2 the log of omega z plus the log of omega p. Okay, it's halfway. It's an average, but on a log scale. So if you undo the logs, do this over lunch, what we discover is that omega m is equal to omega z times omega p square root. Okay, do that over lunch. It's an average, but it's called a geometric mean. It's not the algebra mean, it's the geometric mean. From a geometry standpoint, yes, we're halfway in between. But if you undo the log, you come up with this. Okay, so this is another equation that we're going to need in design. We need to know where we're going to put our maximum phase lead. And then once we determine that, and we know the spread, then that will tell us omega z and omega p. Okay? So we have one equation that tells us how big the phase is, and then we tell another equation that tells us where this peak is going to be. Okay? It's going to be in the middle, geometrically. The other thing that we're going to do is we're going to come back now. Let me go back to the magnitude characteristic and take a look at this phase a little bit more. Okay? Not phase, this magnitude. I'm going to redraw this. I'm going to put this picture on top of this picture so everything kind of lines up. So let's take a look again at magnitude. And this is the magnitude. And this is the phase. This is the angle in degrees. This is the magnitude in dB. And both of these are on the scale with omega. So this is omega z. This is omega p. Comes down here like this. Okay, so we've got some phase lead here. Okay, this is a positive phase. This is positive. This is called leading phase. If you took this compensator and you stuck a sine wave generator on it and then look at the output, you would say, hey, it looks like the output is ahead of the input. That's exactly what that is. We call it a leading phase. It could be in the limit as high as positive 90 degrees. In general, it's a little bit less than positive 90 degrees. Again, it depends on the separation of the pole and zero. Now, corresponding to this picture, in the magnitude characteristic, we have this. Okay, so sketch something that looks like this. And as I said before, the low frequency gain here is K, but we convert it to dB. And we know that this slope is plus 20 dB per decade. Okay, let's do a little bit of algebra. 20 dB per decade. That means if this is separated by a factor of 10, if this is 10 times bigger than this, how much increase do I have here? 20, right? If from here to here is a ratio of 10, then from here to here is a ratio of 20, is 20 dB. So now, look at this geometry. How much gain is here? If this is 20, how much is this? 10. Okay, so this is a useful thing to know. It's useful to know how much gain we have increased right here at omega m. Okay, so this peak right here occurs at omega m. And if we project up in here, we would like to know what is this gain that's halfway, geometrically halfway in between. Okay, So it turns out it's going to be whatever this gain is plus 10 more than that, and it depends on the subray. So you get a formula here that says it's K in dB plus 10 log alpha. This is log, again, all our logs in this class are base 10. So this is the other equation we need to know. All right. So we have several equations. One that tells us how high this how much gain I've got halfway in between here. I've got an equation that tells us how much phase lead I have here. This is theta m. And I also have an equation that tells me the relationship between the zero and the pole and this frequency right here in the middle. All right, so there's 4 equations there. Let's take a look at the circuit. Okay, this is a circuit. And so what I'm going to do is I'm going to draw this diagram, a resistor R1, a resistor R2, and then in parallel with this, I have a cap, a capacitor, like so. This is the output voltage, and this is the input voltage, Vin, Vout over Vn. Okay, so that's the circuit. So let's kind of heuristically analyze this thing. At low omega, at low frequency, C looks like, at low frequency, what is the impedance of this? This looks open, right? So you take that out. At low frequency, C looks open. So V out is going to be less than V in. It looks like a voltage divider. At high frequency, what does C look like? C looks like, this would be the opposite of an open. It looks like a short. Okay, that's what we remember for circuit analysis. The capacitors are shorts at high frequency. And then what happens then is that V out is equal to V in. Okay. So if I look at the magnitude as a function of frequency, at low frequency I get something less than 0 dB, and at high frequency I get a gain of 1, which is 0 dB. And so I get this. Okay. Okay. So we had a, let me review again the lag and put the lead next to it. So this is a review. This is the lag, and this is the lead. The lag looked like this. Okay, again, 2 resistors that look like they're forming a voltage divider, except here C was in series with this leg. With the lead, again, I have 2 resistors. But now the capacitor is in the other leg, and it's in parallel. Okay. And what I encourage you to do is find the respective transfer functions. This is V out, this is V in. This is V out, and this is V in. Find V out over V in. Okay, for each circuit, find V out over V in. That's one thing. It's just a little bit of circuit analysis. I think I asked you to do that earlier with the lag. Go ahead and do that again with the lead. Find equations for omega Z and omega P. Okay, so this is one question, and here's another one. Okay. With this circuit, at low frequency, the capacitor is then open, and then V out is equal to V in, and so we have a gain of 1. With this circuit, at high frequencies, the input and output are the same, and so the gain is equal to 1. So in both cases, the maximum gain is equal to 1. If we want a gain greater than 1, we'll have to add something else either in front or behind, like an op-amp circuit. Okay. So that's the circuit. Notice kind of the similarity. They're kind of like cousins to each other. Just a few resistors and capacitors will do it. Okay, so let's talk a little bit about the design approach. Okay, the design approach. Or before I talk about the design approach, let me talk about why we would use a lead compensator. What was the design rationale? Why would we use a lead? Okay, one of the things that we see is that we can increase the gain at high frequency. Okay, we can increase the gain at high frequency. That means we are basically increasing the bandwidth. Okay? That means we basically can respond quickly. Okay? If we have a control system that's responding sluggishly and we would like it to respond more quickly, then a phase lead makes sense, okay? Because it could increase the bandwidth. It does that by increasing the gain at high frequency. Okay, we can improve the speed of response. Okay. The other reason we use a phase lead is we can increase the phase margin. And that basically helps us, it improves what we call the relative stability. Okay? It improves relative stability. So maybe we have a system that's responding and it's overshooting its mark a little bit, then overshoot, then undershoot, overshoot. And you say, I don't like that overshoot and undershoot. I want to improve the transient response. I want to anticipate what's happening. Then it makes sense to use a phase lead. Okay. Let's sketch a picture, again, reviewing this concept of phase margin. Let's recall phase margin. What is phase margin? Phase margin, which is measured at the gain crossover. So 2 words, phase margin, gain crossover. Let's draw a couple Bode diagrams. These are with respect to frequency. This is the magnitude in dB, and over here this is the phase in degrees. Now, what's important is to figure out the gain crossover. So we look at the gain crossover, and that's where it crosses 0 dB. And so we have a picture of our frequency response. Maybe it looks something like this. Okay. And this is the gain crossover. It's where the gain crosses over 0 dB. And so there's a gain crossover frequency. And then we continue to drop down, and we take a look at where it hits the phase line, and we compare that phase line to, say, 180 degrees. Okay, that's the margin. So the important line here is minus 180 degrees. And so we look at this. Remember, we always draw from the line to the actual phase. And so this is my phase margin. Okay, so this is just a brief review. How do we find the phase margin? We find the phase margin by finding the gain crossover. So where the gain crosses over 0 dB, come down. At that point, we got a gain of 1, and we want to see where we are relative to minus 1. So we want to see, here's gain of 1, here's minus 1, okay? And then we see how close we are by looking at that. Now, let's suppose this is not enough. This is too small. Now, what we will do with the phase lead compensator is we say, we want to raise this up. So what we do is we put a pile of dirt here, okay? You've got a low spot. You've got a low spot in your yard. What do? You fill it in. So that's what we're doing here. We're going to take this lead compensator, and we're going to fill it in. So this is the magnitude, say, of the phase of the open loop. This is the phase of the open loop. And this is going to be the phase of the compensator. We're going to just go put a pile of dirt right here, and we're going to basically lift this. We're going to kind of lift this phase up. But we have to remember that when we do this, this is going to be no longer the gain crossover. What's going to happen is that the compensator is going to add some gain like this. This is the magnitude of C right here. This is the magnitude of G right here. When we add in this 0 and this pole, when we add in this 0 and this pole, we're going to increase the phase right here. That's good. But we're also going to increase the magnitude, okay? And that might be desirable. You might need to increase it, but this is no longer going to be the gain crossover. The gain crossover was here, but when I take the combination of the two, the gain crossover is going to be somewhere out here. All right? And if you look at the gain crossover over here, then you come down here and you say, well, my margin is not here, my margin is here. Okay? So the lead compensator is a little bit more complex to design because omega Z and omega P are chosen right in the vicinity of where we're making our stability margin measurements. Remember, with the lag compensator, we did just the opposite. We figured out where was the desired gain crossover, and we stuck the 0 way over here, a decade below, and then we stuck the pole over here. So with the lag compensator, everything was down here at low frequency. But with the lead compensator, everything is right on top of where we're working. So it's a little bit more complicated. Okay? A little bit more complicated. But we have figured out ways to do this. Okay, so this is the design approach. Let me summarize the design approach. So the first thing what we'll do is we're typically given a high frequency specification. So what we do is we pick desired gain crossover. we pick the frequency that's the desired gain crossover. Maybe we look at our system here and we say, okay, the gain crossover is here. That's the 0 dB bandwidth. But maybe I want it somewhere else. Maybe I want it out here. Okay, I can increase the bandwidth of the system. I can make it respond faster if I let this 0 dB crossover be further over. So the first thing we do is we pick a desired gain crossover frequency. A desired gain crossover frequency is the desired 0 dB bandwidth. Okay. The next thing we do, we have this, maybe we desire to be out here. Then we come down and we look at at that point and we figure out what is the phase margin. Okay. So at the desired gain crossover, we're going to call that omega 1 because it's going to be 0 dB. Okay, so you can call it omega 1. Sometimes in my notes I call it omega 0. This is a gain of 1. This is 0 dB. Okay, so these are the same thing. It just depends on my mood. Today I want to work in dB. Sometimes I want to work in gain. So you pick the desired gain crossover frequency, omega 1, call it omega 0. Understand the concept. Doesn't matter what you call it then. Okay, omega 1. So then at the desired gain crossover, see what is the actual phase margin. Okay, you figure out what the actual phase margin is. So here's the frequency response of the system. Here's 0 dB. Here's the gain crossover frequency. And you say, no, I want the system to respond a little bit faster. This is my desired gain crossover. I come down here and I measure my margin. Okay, the margin at the desired gain crossover. So look at the actual phase margin. The next thing what we do is we say, hey, usually that margin is not enough. Usually that margin is not enough. And I don't have enough margin, so I need to put some dirt on there, so I need to figure out how big theta m is. So what we do is calculate the desired phase lead. How much lead can I get out of my compensator? How much do I need? This margin here is too small. I need to add some dirt. So what I do is I need to calculate theta m. That is going to be the desired margin minus the actual margin. This is not too difficult, just a little algebra step. Maybe I want 60 degrees margin here. I look and see what I have is I got 30 degrees. So what do I need? No, I want 60 degrees here. I only got 30. So I need to get 30 more out of the compensator. Okay. Once we have the desired amount of phase margin, then we can calculate alpha, which is going to be equal to the separation between the pole and the zero. I need to find the ratio of that. And I use that formula that says that that's equal to 1 plus sine theta m over 1 minus sine theta m. All right. So this is one of the formulas that I need. Okay. And this is the other formula that I need. There's two formulas here. But right now, it's just going to give me, I'm going to know what this is, but I still have two unknowns, omega p and omega z. The next thing we do is put omega m on top of omega 1 or omega 0. Okay. Basically what we want to do is where I need the extra phase, I want to put this omega m equal to the right where I want the desired gain crossover. Because that's where I'm making the desired phase margin measurement. And so if I'm going to put a pile of dirt, I need to put it right on top of where I need the phase. So basically what I'm saying is set omega m equal to omega 1. And we have a formula for omega m, and that's equal to square root of omega z times omega p. In some of my notes, I get tired of writing omegas, and so I say omega m is equal to z times p. Okay, I get writer's cramp. Okay. This is omega z and omega p. So now I've got two equations and two unknowns. I had a previous equation that told me that alpha is equal to omega p over omega z. I know alpha because I get that from theta m, from the amount of phase lead I want. It tells me what this is. So this is a known number, but this is unknown. And then I come in and I say, I want to put the dirt right here on top of omega 1. So then this is another known number. So this is known and this is known. And on this side are the unknowns. But now I have two equations and two unknowns. So this is known and this is known. Two unknowns, omega z and omega p. But I have two equations. Okay, so we can solve for it. They're not, okay, we can solve for it. Now the next thing what we do is we have to realize that when we put in phase, the magnitude is also going to be adjusted. At omega 1, study the actual gain. Study the actual gain. So let's go back to this picture right here. Maybe I want my omega 1 to be out here. I want to increase the bandwidth. I want to make the system respond more quickly. So I said, I want omega 1 to be right here. I want this gain crossover to be out here. I said, wait a minute, the gain crossover is here right now. I want it to be here. So that means I don't have enough gain. Okay, so I study the actual gain and see what is the F deficit. Sometimes it's a deficit, sometimes it's too much. Study the actual gain. Okay? And determine the necessary gain adjustment. Okay. So the gain adjustment that we need the adjustment is equal to, it's going to be the actual gain. When we see where we are, this is the desired gain, is 0 dB. This is the desired gain. Remember, what is omega 1? Omega 1 is the desired gain crossover. So at the desired gain crossover, I should have a gain of 0 dB. And I subtract that off of that, the actual gain. And that is the adjustment. This is the adjustment gain desired. How much gain do I desired? How much adjustment do I need? Well, I compare it to 0 dB. If I'm too low, that means the actual gain is going to be something like minus 10 dB, minus 20 dB. I want to raise it up. So minus a minus becomes a plus. In some cases, the gain is maybe too high. Then I got to decrease that. So that's the actual gain. So then what we do is we use our last equation. Remember, what's going to happen is we're going to come into, let me back up a little bit and talk about the concept here. The concept is we're going to go to some place and we're going to put a pile of dirt to get the amount of phase lead. But that's also going to increase my gain. And it's going to increase it by this amount. So what we want to do is we want to make this equal to the desired adjustment. Okay. So what we do is we set the equation, we say desired adjustment, desired gain adjustment, we set equal to K in dB plus 10 log alpha. Okay. We've already, in an earlier step, we picked this. Okay, we picked alpha, so this is a known. We know how much we desire. So now we can solve for K in dB. So do a little bit of algebra, rearrange things. K in dB is equal to the desired gain adjustment. Okay, it's not the desired gain. The desired gain is 0 dB. We want to figure out what is the adjustment. We're going to adjust it with a compensator and subtract off 10 log alpha. Okay, so these two equations are the same. But this was the last equation. All right. That's a good place for us to stop. We'll come in on Wednesday, and we will do a little bit of a design example. If you want to take a look at, get ahead, take a look at the PowerPoint example in this folder. We'll see you Wednesday.